This shows the login and sign up section of our website. A new user will first select to sign up. They will enter their first name, last name, a username of their choice, a password of their choice, and an email. They will then attempt to create their account. If successful, they will be returned to the login page. As we can see within the database, the new user's account has been created. Inside our database, the password that was entered is saved with bcrypt. The new user can now attempt to log into the system. If successful, they will be brought to a dashboard to view all the information and data that is being collected by our system. If they wish to, they can log out with the logout button. The following 3 videos show 3 different tests of the delay of the sound classification. To test this, we have a server post the audio sample to the machine learning server. The time is noted at the bottom right-hand corner. The classification events are timestamped the moment that the machine learning server posts the data to the web server. Due to the computationally heaviness of classification, we wanted to ensure there was not too high of a delay caused with the desire of having a robust system. Our desire is to keep the delay below a 10-second delay. This graphic shows the time delays of their separate posts to the machine learning server. On average, the classification of the audio increases the time from remote server to web server posting of 4 seconds. This is the demo of our classification model. Unfortunately, we've been running into an issue with the audio files coming from our sensor to our server being corrupted. Therefore, to show how our classification model works, we have pre-saved bird calls onto our remote server that will be sent to our machine learning server to be classified. We will first play the audio signal that will be classified. This audio signal will now be sent by a remote server. On the bottom, we can see the machine learning server being run. The machine learning server, using SCP, will copy the file from the remote server onto the machine learning server. It'll then classify it, going through our model, and the data will then be reported to our dashboard. We will continue this for 13 more times, going over 7 species of birds. As the graphic shows, our model trained and tested at 73%. On the small sample size of 14 samples for 7 bird species, our model trained at 92%, going 13 out of 14 correctly classified.
Now I will be showing the over-discharge protection. I'm using a buck regulator to simulate the voltage of a battery, and this meter is connected to the buck regulator, and this meter is connected to the output of the protection circuit. Right now we're at 2.9 volts. I'm going to lower the voltage below 2.5, and you should see the output voltage drop to 0. And there we go, we're at 2.4 volts, and 2.4 volts at the battery, and 0 volts at the output. Once the voltage goes above 2.9, the circuit will continue to output the voltage again. So at about 2.8, 2.9 volts, the circuit turns back on. When the battery reaches 4.2 volts, the charging circuit will turn on the blue LED. And when the battery is below 4.2 volts and is charging, the LED will be off. I have 2 batteries. One is at 4.2 volts and the other is at 2.8. So this battery is at 2.8. This battery is at 4.2. So this is a 4.2 battery. The LED should not turn off. And this is the 2.8 battery. The LED should turn off. Now I will show the DC to DC isolation device right here. This circuit has the isolation device, and this circuit is connected in parallel. With the isolation device, both circuits are able to be powered with one power source, whereas without the isolation device, one circuit gets shorted while the other one gets power. This is the monocrystalline solar panel, and even in low light conditions, it can still charge the batteries. And if I close the solar panel, the charging circuits will no longer receive power. And I will open up the solar panel again. In low light conditions, the solar panel can also power the PCB by itself. As you can see, low light conditions. I will now close the solar panel. And the PCB shuts off. If I open the solar panel again, the PCB will turn on.
All right, go for it. Try it one more time. Hold it. Nice.